All right, so for this problem, we're given this image that has two cables acting on one point. Uh, we have the forces for it's a tension force, but it's given as F1 equals 70 and F2 equals 40. And we're supposed to find the resultant force of F1 and F2, and then the magnitude of the projection of F1 along and perpendicular to this chord AC. And then the last thing we have to find is the angle between them. So I've just written that down here to begin with. The given were the two forces. This is the stuff I just said. And then, so my plan, the first step is always to draw a free body diagram. And then we're going to have to solve for these two forces in Cartesian form so that we can add them together and get the resultant force. And then to get the projection of F1 along chord AC, we're going to have to use the dot product, so we also need Cartesian form for that. To get the perpendicular part, we can just subtract it from the magnitude. We can subtract the magnitude of the projected from the magnitude of the original for F1. And then to get the angle between them, we can just set up the dot product using both definitions as the magnitude of F1 times the magnitude of F2 times cosine theta. That's equal to the scalar sum, so like F1x times F2x plus F1y times F2y plus F1z times F2z. So to get F1 and F2 in Cartesian form, we have to look at the vector of where they act along. So F1 acts along AB, which just by looking at the diagram, you can see that it goes back -2 in the x direction, it goes over 6 in the y direction, and it goes down 3 in the z direction. So that's our AB vector. AC, we can get the same way. So this vector AC goes goes back 4 in the x direction, it goes over 6 in the y direction, and it goes up 1 in the z direction. So that's our vector for AC. And then to turn AB into a unit vector, you just have to divide it by its magnitude here, which is what I did. And this is what I got. So to get F1, which acted along AB, we can just multiply its magnitude, which is 70 newtons, times the unit vector, giving this. And then I did the same thing for AC. I turned it into a unit vector by dividing by its magnitude and got this. And then I multiplied the unit vector by the magnitude of F2, which is 40 newtons. So now that we have both forces in Cartesian form, we can get the resultant force by just adding them since they act at one point A. So I did that right here and got like about -42 newtons, negative 42 newtons in the x direction, about 93 newtons in the y direction, and about like down 24 around newtons in the z direction. So to get the magnitude, you just take the square root of all of the components squared, which was around 105 newtons. So the next part of the question is to get the projection of F1 onto the cable AC, which you can do by using the dot product on the F1 vector and the unit vector of AC, which I did right here. And again, the dot product, one of its definitions is as a scalar sum, so you can just multiply the x's and add them, and then multiply the y components together, add them, and then multiply the z components and add them, and you get around 56.3 newtons. So that was for the parallel projection of F1 on this. So to get the perpendicular part, you can actually just subtract its magnitude. So using this formula down here, you just take the square root of, well, you can think of it like the perpendicular vector is like the vector of F1 minus this projection to get this perpendicular part. So if you take that formula, you can derive this formula, which is just like the magnitude for only magnitude. And so subtracting in this square, the square magnitude of F1 minus the square magnitude of its projection, you get around 41.6 newtons. So finally, to get the angle between F1 and F2, we can use the dot product again. So here I did F1 dot F2, and I used the scalar sum method to get 22,531. And then I set that equal to the other definition of dot product, which is the magnitude of F1 times the magnitude of F2 times the cosine of the angle between them. So I can just solve for cosine, and I got 36.42 degrees. All right, so for this problem, we're given this picture, which has a crate. spring. We're told that the mass of the crate is 40 kilograms, and that this spring, has an unstretched length of 2 meters. So I've just gone and written that down here. So our plan to solve this problem is to first draw a free body diagram, and then we're going to use the equations of equilibrium to solve for the force that has the spring in it, and then we can use the definition of a spring force being F equals kx, where k is the spring constant and x is the length of the spring from its unstretched position. So here's my free body diagram. Because we're given the lengths, I was able to solve for the angles. So since this is 2 and 2, this angle is 45. And then here I just used the inverse tangent of these side lengths to get the angle here. So the weight force, we're given the mass of the, what is this, a crate? We're given the mass of the crate, which is 40 kilograms. So to find the weight force, it's just going to be F equals mg, where g is 9.81 meters per second squared. So multiplying those, we get 392.4 newtons down. So now we can start setting up our equations. So the first one I did was the sum of the forces in the y direction is equal to 0. So I have my weight force, and then I have FDC is this one here. So I'm solving for this vertical length using hypotenuse times cosine, because in this case cosine is adjacent over hypotenuse. And so I get this expression relating FDB and FDC. So to solve this system of equations, we need one more since we have two unknowns. So I set up the sum of the forces in the x direction is equal to 0. So that's going to be this minus this. And since those are the only two, they're going to be equal because they're in opposite directions. So and that gives me this. That gives me this equation relating dB, FDB and FDC. So now I can solve the system of equations, which I do by plugging in, I plug in FDB from this equation into FDB into this equation. And getting that, I can just get an expression with FDC, and so I can solve for FDC, which was around 333 newtons. And then I plug that into the equation that I found here, and I can solve for FDB, which has our spring. So the force in the spring is 283.188 newtons. I set that equal to, well, first I had to find the distance from unstretched of the spring, basically, right here. So the spring is stretched this way. We're told that the unstretched spring length is 2 meters, but actually solving for this length, it is 3.61 meters. So the distance from equilibrium is just subtracting the unstretched from its actual length, which was 1.61 meters. So then I could plug that into F equals kx and solve for k, which I did right here, and I got 175.89 newtons per meter. All right, for this problem, we're given this picture, and we want to find the force in each rope needed to support a 20 kilogram flower pot. And then the second part is if each of these if each of these wires can hold a maximum tension of 50 newtons, find what the greatest weight force that the system can support is. So I've just written that down. And our plan to solve this is to first draw a free body diagram, which I did right here. And then in this case, we want to find angles to the axes instead of finding these forces in Cartesian form, because it'll save a lot of time. Like this rope here acts pretty much parallel to the y-axis. So there's just one angle that we can draw that lets us use it in our equations of equilibrium. And we can do a similar thing with the other two ropes. So we want to find those angles, and then we want to use the equations of equilibrium, solve for our tension forces. And then for the second part of the problem, we're just going to use the equations that we got in the first part, plug in 50, which is the maximum, and instead solve for W instead of plugging it in. So right here, I'm solving for the angles. To find this one, we have this rope, and then we're given all of these distances, so we can just do the inverse tangent of 6 over 3. I got 63.43 degrees. And then I did the same thing for both of these. These two triangles here are actually the side lengths are exactly the same. So the angle that I called alpha is equal to the angle that I called beta, which is 26.57 degrees. So the next thing I did was solve for the weight force. We have the mass, so weight force is equal to mass times gravity, which was 196.2 newtons. So now that we have everything, I started setting up my equations of equilibrium. The first one that I did was the sum of the forces in the z direction is equal to 0. So for that, we have the weight minus 196.2 newtons. And then we have this component of FAB. So to get that, we can just do the hypotenuse times sine of this angle. And doing that, I can solve directly for FAB, which I got as 219.368 newtons. The next equation I set up was the sum of the forces in the x direction is equal to 0. So that's going to be this component here and this component here, which are equal and opposite each other. And because the angles are the same, it's just going to be FAC equals FAD. So the next equation was the sum of the forces in the y direction. And for this, it's this one of FAB in the negative y direction. So I plugged in the hypotenuse of FAB, which was 219, and I used the cosine of the angle to the y-axis to get its y projection. And then because FAC and FAD are equal, I can just I didn't do FAC plus FAD. I just did 2 times FAC cosine of the angle to get the y projection, and that way I could solve for FAC, which was 54.854 newtons, which is equal to FAD. So for the second part, we're told that the maximum tension the ropes can hold is 50 newtons. So if we just I used the equation that I got earlier in part 1 using the sum of the forces in the z direction. So instead of using negative 196.2, I just used negative W for the weight force. And then I just used the rest of the equation as normal. I used 50 instead of FAB because it's given. So plugging all those in, you can just solve directly for W, which was 44.719 newtons. So it wasn't asked, but I just wanted to see what this was in kilograms. So using the weight equals mg, I just divided by 9.81, and it was 4.6 kilograms. So the 20 kilogram crate from part 1 might have been a little bit unrealistic. So for this problem, we're given these 3 forces, 450 newtons, 300 newtons, and 700 newtons that act along this beam, and we are asked to find a single resultant force and where it acts. So to do this, first we're going to draw an FPD like always, and then we can sum together all the forces in the x and y directions to solve for FR, the resultant force. And we're also going to get the moment from A, which is all the way on the left, sum all of them to find the resultant moment, and then to find the distance at which this new force acts at with respect to A, we can just set up the moment is equal to FD. The negative is just to take into account the direction of the moment, but we can just plug everything in and solve for D. So here's my free body diagram. I did nothing with the supports because we don't need them in this problem. We're only concerned with these external loads. So the first thing I did was find the sum of the forces in the y direction. So this force here is 450 newtons. So to get the y direction, we can just do 450 times sine of 60. This one is straightforward, it's just 300. And then to get the y direction of this, we can just do the cosine of 30. So summing those together, I get negative 1295.9 around newtons. So I did the same thing in the x direction, using cosine instead of sine. For this force, this one has no x direction, obviously. And this one I can just use the sine of 30, and I get negative 125 newtons. So putting these two together, this is technically a vector in Cartesian form of the resultant force. So here is the sum of the moments. So the sum of the moments from A, so the first one is going to be this 2 meters times the y component, which we said was negative 450 sine 60, and that causes a clockwise moment, so it's negative. The next one is 2 plus 4 meters for the moment arm, and then down 300 newtons, and that's again a counterclockwise rotation, so it's negative. This one, same deal. 9 meters over and 700 cosine 30 down, negative. And then we're given this negative moment, 1500 newton meters already. So add that as well, sum them together, and I got around 9,500 newton meters in the clockwise direction. So to solve for the distance away from A that the force acts at, we can use the definition of a moment, which is what we were doing before. It's just the moment arm times the force perpendicular to the moment arm. So in this case, we have a distance d, which is our moment arm, and then we have the y component of our resultant force, which we already have. And because this causes a clockwise moment, we just have to set mr to negative on this side of the equation. So we already have the y component of fr since we solved for it, and it was around negative 1300. So I just plugged everything in here, solved for d, and I got around 7.4 meters. All right, for this problem, we're given this beam that has like a bent rotation in it. We're told that this distributed load is 3 kilonewtons per meter, and we want to find the reactions at A and B, the supports. So to solve this problem, first we're going to draw a free body diagram like always, and then we're going to use the equations of equilibrium to solve for those support reactions. So pretty simple. Here's my free body diagram. So the first thing we want to do is replace this distributed load with just a single force in the y direction. So to do that, you just have to multiply the distributed load, which is 3 kilonewtons per meter, times 4 meters. It's kind of like solving for the area inside of this square. So doing that, we get 12 kilonewtons, and it's going to act at the centroid of this shape, which it's rectangle, so exactly in the middle, which is 2 meters apart on this right beam. Another thing of interest from the free body diagram is this angle, 30 degrees. Because this support is I believe it's a roller, so it just has a normal force that goes perpendicular to this like bent. It's not really like it's basically like thinking this is like the angle the ground is at, and this is the normal force perpendicular to it. So if you think of this as rotating down to this part being flat, this angle disappears. And so this angle is going to be so that angle is going to be equal to the angle of the incline. So I think we're ready to use our equations of equilibrium, and since we have 3 unknowns, the first thing you always want to do is a moment, and so I chose the moment about point B because there's 2 forces there that we can ignore, so we can just solve for the third, which is AY. So to do this, you just sum together all the moments. This first one, 2 times 12, is going to be this moment, which acts counterclockwise, so it's positive. The next one is to the it is to this distance here, and then this component of AY. That component. So that distance, this distance is going to be equal to, we know that this length is 3. So to get this part of the triangle, you can just do the hypotenuse 3 times sine 30. So multiply that by AY sine 30, which is the x component, and we can get that moment, which is clockwise, so it's negative. And then the final moment is going to be 4. The moment arm is 4 plus this distance, which is going to be 3 cosine 30. And then this part of AY, which is AY cosine of 30. So sum all of those together equal to 30. We can get AY is equal to 3.713 kilonewtons. And the rest is easy. We can just use, I used the sum of the forces in the y direction first, which is just By minus 12, and then plus this component of AY, which we can get with cosine 30. And then adding all those together to solve for By, we can get 8.784 kilonewtons for B sub y. The last thing you have to do is sum the forces in the x direction, which is this support I said was negative in the negative direction, so negative Bx, and then this component of AY that acts in the positive x direction. So because we already know AY, 3.713 sine 30, we can use that to solve for Bx, which was 1.857 kilonewtons. All right, for this problem, we're given this pipe assembly. We're given these forces. There's a 400 Newton force, a 500 Newton force, and a 600 Newton force. And we want to calculate the reactions at the fixed support A. So I've written that down. Our plan is to first draw a free body diagram like always, and then use the 6 equations of equilibrium for 3 dimensions that we have, which are the sum of the forces in the x, y, and z directions are equal to 0, and then the sum of the moments about the x-axis, the y-axis, and the z-axis are all equal to 0 as well. So here's my free body diagram, and because it's a fixed support, it has no axes or like rotations that are free available to it. So there's going to be a support reaction in all 3 directions and a support moment in all 3 directions. So there's 6 unknowns that we have to find, which is perfect because we have 6 equations. So the first one that I did was the sum of the forces in the x direction, which is just AX, the support in the x, and then minus 400. It's kind of cut off on the side, but it's one of the forces that we're given. So we can solve directly for AX, which is 400 newtons. In the y direction, it's a similar thing. We just have the support AY, and then we have this 500 Newton force. So we can solve directly for A sub y, which was 500 newtons in the negative y direction. In the z direction, we just have the support AZ, and then we have the given force down 600 newtons. So AZ minus 600, AZ is just going to be 600. So we have all of the support forces, we just need the support moments now. So to get the sum of the moments around the x-axis, which is this axis, there's 2 directions of forces that we have to watch out for. So we have a moment caused by this. Or no, sorry, I apologize. We have a moment caused by this, which gives a clockwise moment about the x-axis, so that one is negative. That was this one right here. So the moment arm was 1.25 because this is 0.75 and this is 0.5. Then the other moment is this distance out and then down. So from this 600 Newton force, the moment is going to be 1 meter and the force down is going to be 600. And then you have to add the moment from the support, since that's what we're solving for. And I just arbitrarily said that it was in the positive counterclockwise direction. So solving for MAX, we get 1,225 Newton meters. So to solve for the moments about the y-axis, it's the same deal. This is the y-axis. That's a bad. Okay, this is the y-axis. There's going to be one moment caused by that moment arm and this 400 Newton force, and that is a rotation that is negative because it's clockwise about the y. So that one is negative here. And then the other moment is from the 600 Newton force, this 0.75 meters over, and then 600 Newtons down. And that's the same deal. It's a clockwise moment, so it's negative. Add the moment from the support and solve, and we got 750 Newton meters. So the last one is the sum of the moments about the z-axis. And in this case, there's no forces that are perpendicular to it and away. So in this case, it's just the moment from the support and nothing else. It's just equal to 0. So that one is 0. All right, for this problem, we're given this truss. We're given these 4 forces, 1.5 kilopounds, 2 kilopounds, and then 2 3 kilopound forces. And we want to find the force in members AB, AI, ED, and EF. So I've written that down here, and the plan to solve this one is to first draw a free body diagram, like always, and then, a global free body diagram, because it's a truss. First, we're going to try to analyze the entire thing. We're going to try to plug stuff into our 3 equations of equilibrium in 2 dimensions. And then after that, we're going to cut this truss apart, which is called the method of sections. And then for each thing that we cut, we're going to draw a free body diagram and then use our equations again to solve for the forces. So here's my free body diagram. The first thing I did is we have to solve for these supports. So here there's a support in the y direction, and then at E, because it is a pin, there's going to be a support reaction in the x and y direction. So because there's 3 unknowns, we want to start with a moment, and I did that at E, so we can ignore these 2 support reactions here. So some of the moments about E is going to be this first moment, which is 10 feet times 3 kilopounds, and that is counterclockwise, so it's positive. And then 10 plus 10 is 20 times 3 kilopounds, and again, that's going to be positive because it's counterclockwise. We have all the way over here 40 feet, and then the support reaction we're trying to solve for, AY, that is clockwise, so it's negative. And then the final 2 forces, we have 4 feet times this 1.5 kilopound force here, and that is clockwise, so negative. And then finally 4 plus 8, 12 times the 2 kilopound force, and that is also clockwise and negative. So summing all of these together, we can solve for AY, which is 1.5 kilopounds. So now that we have one of these supports, we can plug it into the other 2 equations. So the sum of the forces in the y direction is going to be equal to AY, which we solved for 1.5 kilopounds. We have minus 2 3 kilopound forces in the y direction. And then the final one, the final support, E sub y that we're solving for. So summing those together, we can solve for E sub y, which is 4.5 kilopounds. The last equation of equilibrium, the x direction, we have a 2 kilopound force, a 1.5 kilopound force, and then in the negative x direction, which we just defined arbitrarily, the support at E sub x. So solving for that, we can just get 3.5 kilopowns. So we have our support reactions from analyzing global equilibrium, but now to get, we need AI, AB, and ED, and EF. So to get these, we can just cut through the truss. So first, we're just going to cut through here. And then doing this, we can draw a free body diagram of this point A, which I did right here. So because these members are cut, they can just be treated as forces. And we're just going to say that every force, or we're just going to assume that every force acts in tension, so away from joint A. And the first thing I needed to do was solve for this angle theta, which I did by using the tangent of these 2 side lengths. So we know that it's 4 feet up and 10 across. So using the tangent equals the opposite or the adjacent. Using the inverse tangent, so I'll get 21.8 degrees. And then I just set up the equations of equilibrium. So in the y direction, it's 1.5, the support reaction at A, AY, plus this vertical component of AI. So to get that, you can just do AI times sine 21.8. Summing those, we can get AI is equal to negative 4.04 kilopounds. And so we assume that the positive direction of all these forces was in tension. So if any of them were negative, we know that they're in compression. So AI is in compression. And so then I did the sum of the forces in the x direction, which is AB plus the component of AI that also goes in the positive x direction. So when we set this up, we assumed that everything was in tension. So things that are in compression are negative. So we still want to add this, but because it's negative, it ends up being subtracted, if that makes sense. Hopefully it does. But that's why it's AB plus this, which happens to be negative 4 point whatever. So doing that, we can solve for AB, which is 3.75, and because that's positive, that's in tension. So to get EF and ED, you do the same thing. I just cut the truss right here so that I can model point E as a particle, essentially, with EF and ED coming out as forces. So these dimensions are exactly the same. So the angle is exactly the same here, 21.8 degrees. I did the same thing. I summed the forces in the y direction, 4.5, the support from E, and this component of EF, which you can get from EF times sine 21.8. So doing those, adding those together, I got EF was equal to negative 12.12 kilopounds, and since it's negative, it's in compression. For the sum of the forces in the x direction, it's negative 3.5, the support at E, and then minus ED, which is only in the x direction, and then minus this x component of EF, which is EF cosine 21.8, and the same deal before. We assumed that they were in tension, so a positive would be like negative, and since we got negative here, we can just plug it in. It turns positive, and so you add it. Solving for ED, we get 7.75 kilopounds, and because it's positive, it's in tension. All right, for this problem, we're given this truss, which has an 8 kilonewton force and a 4 kilonewton force applied to it. And we want to find the force members AF, BF, and BC, and whether they're in tension or compression. So I've written that down here, and the plan is to first draw a global free body diagram. We're going to use the equations of equilibrium and try to solve for the reactions of the supports. We have a pin here, which is going to have a reaction in the x and y directions, and then at B we have a roller, so just a support going up in the y direction. Next, we're going to use the method of sections and cut this truss in half, basically, draw a free body diagram, and solve for the three forces that we want, which just so happen to be right here. So we're going to cut through like that. Anyway, I'm getting ahead of myself. First, we need to analyze the global equilibrium. So since we have three unknowns, we're going to start with a moment, and I did the moment at A since that's where we have two unknowns. Doing that, the first moment is this distance 1.5 times the force By, and because that is counterclockwise, it's positive. The second moment was this 2 meters minus this 8 kilonewtons, which is clockwise, so it's negative. And then 2 plus 2 times 4 kilonewtons for the final clockwise or negative moment here. Summing all of them together, we can solve for By, which was basically 21 and a third kilonewtons. The next equation, the sum of the forces in the y direction is equal to 0. For those, it's just going to be Ay and By. And so since we just we solved for By, we can plug that in. And the only other one is Ay, so it's just going to be negative, or in the other direction. The sum of the forces in the x direction is these two, 4 and 8 kilonewtons, and then the support reaction at A. So summing all these together, we can solve for the support at A. Ax equals negative 12 kilonewtons. So now we're going to apply the method of sections. So we want these three forces, basically, which is convenient because we can just cut through all three members here and then draw the new cut truss we can draw those cut members as forces. So we're going to model all of them. We're just going to assume them as all being tension forces. And then if we get a negative force, we'll just say that it's in compression. So here we have three unknowns. So the first thing we want to do is a moment in our equations of equilibrium. I did the moment about B, and the moments are this length, 1.5 meters, times there's one force down going this way, which will create a counterclockwise positive moment. And then this one going up here, 1.5 times AF, which we want to solve for, and that is clockwise, so it's negative. Adding those together, dividing, you see that AF is 21⅓ kilonewtons, and since it's positive, it's going to be in tension. So next, I did the sum of the forces in the x direction, which are 12 kilonewtons left from the support at A sub x. There is a x component parallel, or sorry, there is an x component of BF, and so to get that, we need to find this angle that acts BF between BF and the x-axis. So to do that, we can just use the tangent being opposite over adjacent, and the side lengths. This is 2 meters, this is 1.5 meters. So if we do the tangent inverse, we get 53.13 degrees. So back to the sum of the forces in the x direction, we can subtract BF cosine of 53.13, solve for BF, which was negative 20 kilonewtons, and because it's negative, it's going to be in compression. So finally, I summed the forces in the y direction, and that is this 21.333 down from AY. There's 21.333 up from BY, so those two cancel out. There is another 21.333, which is from AF. And then finally, this y component of BF, which is BF sine theta. And because it's negative 20, even though this is going up, we can just plug in the negative, and it becomes negative 20 sine 53.13. The last support that we want to solve for, BC, summing all those together, we can solve for BC, which is negative 5.33 kilonewtons, and because it's negative, it's in compression. All right, for this problem, we're given this frame. We are given that it has a distributed load of 200 Newton per meter, and there's another force of 800 newtons acting along the x-axis. So what we want to find is the resultant force of the reactions at A, B, and C. And so, to do that, we are going to first draw free body diagrams of each body of the frame. We're going to use our equations of equilibrium to try to find equations that we can plug into other parts of the body. So if we analyze this in global equilibrium, there's going to be 4 unknowns because there's a pin at A and a pin at B, and there's only 3 equations of equilibrium. So there's nothing we can actually do at the global scale. So we're just going to save ourselves time and split this into 2 parts. This part that is angled at 60 degrees above the ground, and then this like half of a square shaped looking part. So here I did the angled body first, and the first thing I did was replace the distributed load with a single force that acts in the middle of it. So to do that, I had to get the length of the angled body. So the height is 2 meters, and we have the angle, which is 60 degrees. So I just did sine 60 is going to be equal to opposite over hypotenuse, so 2 over the length. Doing that, I got 2.31 meters. Multiplying 2.31 times 200 newtons per meter, I got 462 newtons, which acts perpendicular to this 1.155 meter length, which is just half of the 2.31. So this is the replaced free body diagram that I drew to replace the old one. And there's still not much we can do. There's still 4 supports. So again, we only have 3 equations. So we can't solve for any of these straight up. So the only thing that we can hope to do really is get an equation that has C. So C is the pin that connects both of the 2 bodies of the frame. So if we use the moment at A to ignore AY and AX, we can just get an equation that has CY and CX in it, and then we can plug that into our other body. So that's what we're trying to do. The moments about A, there's going to be one caused by this distance and the force going down. So that is, oh, sorry. Because this force acts perpendicular, we can just say that it's 1.15 times 200, and because that is a clockwise moment, it's negative. And then there's going to be a moment caused by this 1.155 and this CY vertical component of the pin at C. And then there's going to be a moment caused by this 2 meters and CX, which is again going to be, oh, sorry, no, this one is, no, that is counterclockwise, so negative. So adding these together, we get this equation, 2CX equals 1.155 CY minus 0.61. And that's all we can get, but we can plug that into our second frame down here. So here's the free body diagram. And I did a similar thing where I want to find an equation with CX and CY to relate to this other one that I found. So doing that, I did the same thing. I summed the moments at point B to ignore BY and BX, the 2 support reactions. And doing that, it's going to be 2 times 800 for a positive counterclockwise moment. And then this 2 meters times CY, which is positive, and then 2 meters times CX, which is positive. So adding all these together, we get another equation, 2CX equals negative 1600 minus 2CY. And I just plug in the old equation into the new equation, and I get CY equals negative 338 newtons. So all that means is the directions of CY, CX, and CY that we got were wrong. The assumptions were wrong. To get the resultant force, it's just going to be the magnitude of the vector CX comma CY, basically. So the square root of the CX squared plus CY squared, which is 572.44 newtons. So now that we have CX and CY, we can go back to the original body and use the other 2 equations of equilibrium, like the sum of the x and the x and the sum of the forces in the y. We can do that now. So down here, that's what I did. It's negative 338 from pin C plus AY minus this force here, cosine 60 to get the vertical component, and doing all that, we solve for AY, which is equal to 569 newtons. In the x direction, it's the same idea, negative 462, which is the support at CX that we found, plus AX, the support at A, and then the x component of the resultant force from the distributed load. Summing all those together, get negative 61.896 newtons. And then the same deal, to get the resultant, we are just going to do the square root of the component squared. And doing that, I got 572.36 newtons. So now finally, we're going to go back to the second segment or body and do the same thing, plug C into equations for the forces along the x and y directions. Doing that, this one is much simpler since it's only in the x and y. We have by minus cy. Cy we found was negative, but it doesn't matter. So plugging all that in, we got by equals negative 338 newtons. And for the x direction, it's the same thing. We have positive bx minus cx, Cx was again negative, so Bx is going to be equal to 338 newtons, and the resultant is the square root of the square of the sum of the square of the components, which is equal to 478 newtons. All right, for this problem, we're given these two blocks. There's a force at an angle of 30 degrees from the y-axis, and we're also given that the mass of both of these is 5 kilograms. So we want to know what the largest force P is that we can apply at C without either of these blocks moving. So because we're not given like the width of any of these blocks or any of the distances, the only thing we can really do is assume that they're going to slip. First the plan is to analyze joint C at the middle, which is where the force acts, and the plan is to draw a free body diagram like always, and then we're going to use our equations of equilibrium to try to get these forces going into the blocks. Sorry, forces of the compressive elements going into the blocks. So, and then we're going to analyze each block, and because we can only analyze slipping after drawing a free body diagram, of course, we can set the friction force equal to the coefficient of static friction times the normal, and the coefficient of static friction is given in the problem as 0.5. So we're going to do that for both blocks, so let's just get started. The first thing I did was draw a FBD at point C. Here's the force P that acts at 30 degrees, and these two forces are for the compressive elements that go into blocks A and B. So setting up the equations of equilibrium, we have the sum of the forces in the y direction is just going to be P cosine 30 to get this part of P on the y-axis, and then minus this y component of AC, so AC sine 30. Setting those equal to 0, we can solve for AC, which is negative 1.732 P. So it's important that it depends on P because at the very end we're going to solve for it. Setting the sum of the forces in the x direction, we have this component of P that goes in the negative x direction, so negative P sine 30. We have negative BC, this acts entirely along the x direction, and then in the positive direction we have this x component of AC, so AC cosine 30. So then summing all of those, we get BC is equal to negative 2P. So here's my free body diagram for block B. We found that BC, we modeled it as going to the left, but we found that it was negative. So it's actually going to the right, but these two forces should be equal and opposite. So if this one up here is going to the right, this one down here should be going to the left. So because this force is going to the left, there's going to be a friction force opposing it along the incline. So this friction force is angled at 30 degrees because there's a 30-degree incline. To solve for the weight, we know that the mass is 5 kilograms, so 5 times 9.81 meters per second squared is equal to 49.05 newtons down. So now we can start analyzing this. The sum of the forces in the y direction, we have the weight, negative 49.05. The friction force, there's going to be a y component of that, so negative FR sine 30 to get this component. We have a normal force, which acts perpendicular to the incline, which is also going to be angled at 30 degrees. So that's going to be plus n sine 30, plus n cosine 30 to get the y component. Summing all of these, we can solve for n in terms of F of R, which is a friction force right here. What I did then was sum the forces in the x direction and set that to equal. We have the force from joint C, 2p, negative 2p because it's in the negative x direction, the x component of the friction, FR cosine 30, and then n sine 30 to get the x component of that. Summing all of these, we can solve for the friction force in terms of P and N, which is this. So now we have two equations that and two unknowns, so we can plug them into each other and solve, which is what I did right here. I plugged in, I had this equation, n is equal to 56 blah 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 plus 0.577 FR, and FR is equal to this, so I plugged that in. Worked everything out, and I got this. The normal force is equal to 42.489 plus P. So because we can only analyze this assuming slipping, we can say that this friction force is going to be equal to the coefficient of static friction times the normal force, which, if this is n, then the friction force is half of that. So 21.245 plus 0.5 P. And then plugging in the other equation for FR that we had up here, plugging that into the equation that we just got down here, solving everything out, we get P is equal to 37.144 newtons. So now we just need to analyze the other block and see which value of P is smaller, because that'll be the largest force before anything moves. So here's block A, which is just flat against the ground. Earlier we said that there would be a force going down to the right, which ended up being negative, so there's actually one going up to the left. So on the block, because these forces should be equal and opposite to each other, this one is going to be going down and to the right. To solve for the weight force, it's the same exact thing. It's actually the same way as before, so I didn't bother. It's just 49.05 newtons. Setting up my equations of equilibrium, the sum of the forces in the y direction is equal to the weight, negative 49.05, plus the normal, which is only in the y direction this time, and then this y component of the compressive force, 1.73 P. Summing all of those, I got the normal is equal to 49.05 plus 0.866 P. We can go straight to slipping now, set that equals to the coefficient of static friction times the normal force, which in this case is going to be 0.5 times n. Solving for the sum of the forces in the x direction now, we have the friction force, which goes in the negative x direction, which we just solved for, and then or sorry, no, we're going to plug that in later after we solve for it. But we have the friction force going in the negative x direction, and then we have this x component of the compressive force, 1.732 cosine 30. So adding those together, we get the friction force is equal to 1.5 P, and then plugging that into here, we can solve for P, which is 22.99. So because this value of P is smaller, this is the largest one before anything will move. Like if this is the force where something moves, I mean, at 37 newtons, this one has already moved. So that's why this is the answer. All right, for this problem, we're given this contraption and we want to find the internal forces in moment at point C. So we're given this 50-pound force down. There's a negative 100 pound-foot moment going clockwise. And I think that's everything we need. So the plan to solve this is to first draw a free body diagram like always. First, we're going to draw a global free body diagram so we can solve for the support reactions. And then we're going to cut the beam at C because we want to analyze the internal forces. And we're going to solve for the shear force. There's going to be a normal force, and there's going to be a bending moment using the equations of equilibrium. So here is my global free body diagram. Analyzing this in the y direction, we have the support at AY, and then this negative 50 pounds downwards. So AY is just going to be equal to 50 pounds. In the x direction, we just have the support AX and BX. So those two are going to be equal to each other in opposite directions. So I did the moment at point B, and that's equal to this 2.5 moment times the support A of X, which is a counterclockwise or positive rotation. And then the other moment is going to be this 12-foot distance and this 50-pound force down, which is clockwise, so it's negative. So summing those together, we can solve for the support AX, which is 280 pounds. So next, we cut the beam at point C. draw a free body diagram, which looks like this. These are the support reactions AX and AY, so 50 pounds up and 280 pounds to the right. There's going to be a shear force going down at the edge of where we cut. There's going to be a normal coming out, and there's going to be a bending moment, which helps to hold the beam still. So we're going to do the same thing. We're going to use the equations of equilibrium. In the y direction, we have the 50 pounds from the support A, and then minus the shear going down. So the shear is just going to be equal to 50 pounds. Summing the forces in the x direction, we have 280 pounds, the support at A, plus the normal, which goes in the same direction. So this normal is going to be equal to negative 280 pounds, or 280 pounds in the negative x direction. To get this bending moment, I summed the moments from point A, which is equal to this 3-foot moment arm times the shear force, which is going to create a clockwise or negative rotation. And then we just add the bending moment, which we defined as counterclockwise, so it's positive. So using that, we can solve for it, and we got 150 pound-feet. All right, for this problem, we're given this beam that has a 15 kilonewton force, a negative 20 kilonewton meter moment, and then a 10 kilonewton per meter distributed load. So we want to find shear and bending moment diagrams, and to do this, first our plan is to draw a global free body diagram, use the equations of equilibrium to solve for the support reactions, which will help tell us what the endpoints of our diagrams should be, basically. And then we're going to draw free body diagrams for all of these segments before these important points, like where these forces are applied. Like there's a force down at 2 meters, so we're going to want to cut before then and analyze and see what happens. We're going to want to cut after that, but before the moment to see what happens. We're going to want to cut before the distributed load and see what happens, and so on and so on. So here's my global free body diagram. The first thing I did was sum the forces in the y direction. So the support AY, minus 15 kilonewtons down, minus there's going to be a distributed load. This is 2 meters times 10 kilonewton meters, so negative 20 down, and then plus the support at B, By equals 0. So doing this, you can solve for AY, which is equal to 35 minus By. Then I solved for the moment about A. So there's going to be a moment of 2 meters times 15, which is in the clockwise direction, so it's negative. The next one is this resultant force happens exactly at the centroid of where it acts. So this is a beam, so it's a square, so exactly in the middle. Or it's a rectangle, sorry, so it's in the middle. So this is going to be a 2, 3, 4, 5 meter moment arm, and then the 20 kilonewton force. And again, that's clockwise, so it's negative. And then finally, the entire moment arm, the entire beam, 6 meters times the support reaction By. So doing that, we can solve for By, which is 25 kilonewtons, and then we can plug that into this formula and solve for AY, which is 10 kilonewtons. So the first thing we want to do is, like I said, cut this beam before the first force and see what the shear and moments are. So from 0 to 2 is the first segment, and we have the 10 kilonewton force up, a shear, and a bending moment. We can ignore the normal force because the support AX is just 0. There's no other forces in the x direction. So the normal is not important. We don't even want to, we don't care about it at all. It doesn't help. So anyway, what I did here, there's just a 10 up and a V down. So the shear is just equal to 10 kilonewtons here, constant. Summing the forces, I got the moment is equal to this times the shear. So that was 20 kilonewton meters, 20 kilonewton meters. And the definition of the moment is that its derivative is equal to whatever the shear is. So because the support reactions at A and B don't have a moment, they're pins. The moments are going to start at 0. So its derivative is 10, so it's going to go from 0 to 20, which makes sense if the slope is 10. It's consistent, basically. The next segment is, well, it's still from A, but it's a minimum of x equals 2 to a minimum of x equals 3, like how long this distance is. So doing the same thing, I summed the forces in the y direction and got the shear is equal to -5 now. So the moment I solved for it over here the same way as always, and I got 15. And its derivative is going to be the shear, which is -5. So we expect the moment so far to go up from 0 to 20 and then start linearly decreasing to 15. The next segment is from 3 to 4, and that's after this clockwise moment. So there's no more forces in the y direction, so the shear is still -5, nothing changed. Solving for the moment, we get that it's 30 kilonewton times meters, which means that at this point, at x equals 3, the moment should jump up, and then it's going to keep decreasing to 30. So it's going to jump up to 35, and then its slope is -5, so 1 meter later it's going to be at 30, which is consistent. Finally, for the last segment, we don't even need to do anything, really. The definition of the derivative of the shear force is like the distributed load in kilonewtons per meter. So because that's -10, we know that the shear is going to be basically the integral of this, and the integral of -10 is -10x. So it's, I believe we were at -5. It's going to decrease at a rate of -10 per meter to -25, and we know it's going to go to 25 because that was the support at B, 25 kilonewtons. So because it's negative, we know it's going to keep decreasing to -25. Similarly, we can do the same thing for the moment. We know that the derivative of the moment is the shear, which we said was approximately -10x. There's going to be some plus c that we don't care about. So this mx is going to be some function that looks like -10x squared, because that's the derivative of -10x. Really, it's going to be over 2. I didn't put that, but what matters is the shape of the graph. And this is an exponential decay. And because it's -x squared, which looks like this, it's going to be this part of it, which is concave down. So putting everything together, here are the two graphs. So excuse me. So from 0 to 2, we said that the shear was equal to 10, so it's just going to stay at 10. Then from 2 to 3, we saw that it dropped to -5, and it stayed that way until x equals 4. And then from 4 to 6 is where we have a distributed load of -10. So 4 to 6 is 2 meters, so that's going to be -20, and we're at 5. That takes us to -25. For the moment diagram, we saw from 0 to 2 that it goes from 0 to 20 linearly. And then from 2 to 3, we saw that the linear slope changed to -5, so it decreases from 20 to 15. At x equals 3, there's a 20 kilonewton meter moment, so it jumps up to balance that from 15 plus 20 to 35. The slope is still -5 from the moment being at from the shear being at -5. So it drops by 5 from 35 to 30. And then here's the exponential concave down decay back to 0. All right, for this problem, we're given this assortment of shapes, and we want to find the location of the centroid, but only the y location of the centroid. So to do this, we want to find the area, the distance to each of these segments centroids, and we want to find the area times that distance, because to find the centroid, it's going to be the sum of the area times the centroid divided by the sum of the area. So here I made a table to find all these, I call this segment 1, this segment 2, and this segment 3. So segment 1 has an area of 150 times 15, which is 2250. Its centroid is going to be right here in the middle, which is 100 plus 150 plus 15 over 2, which is 257.5. Multiplying them together, we get this. For segment 2, its area is also going to be 150 times 15, 2250. Its centroid also acts in the middle since it's a rectangle, so that's going to be 100 plus 150 over 2, which is 175. Multiplying the 2, we get this insanely large number. For segment 3, which is the circle, its area is pi r squared. The radius is 50 millimeters. So in that we get about 7,800 millimeters squared around. Its centroid is going to be in the middle since it's symmetric. So just the radius is going to be the distance off the x-axis, 50 millimeters. So summing all the areas together, I got 12,353. And summing the areas times the distance to the centroids, I got a crazy huge number, like 136,000. So to get the centroid, you just divide the area, the sum of the area times the centroid, divided by the sum of the area. And I got 110.6 millimeters, which is from the bottom. I don't know why this answer is measured from the top, but to get it measured from the top, you could just get the total height, which is 100 plus 150 plus 15, which is 265, minus the distance of the centroid from the bottom, which I measured as 110, and then we get the 154 that they have. All right, for this problem, we want to find the moment of inertia of this area about the x and y axes. So in this problem, we're given that the equation of this top line is y squared equals 2x, and the equation of the bottom line is just y equals x. So our plan to find this is to find a differential area in terms of, basically, if to solve these problems without having to use the parallel axis theory, you want to find a differential area that is parallel to the thing that you're trying to find. So if we want to find the moment of inertia about the y-axis, you want to use a differential area that's parallel to it. So the next step is to use the formula. The moment of inertia about the y-axis is the integral of x squared dA, and for the moment of inertia about the x-axis, it's going to be the integral of y squared dA. And for that, we're going to have to find a different differential area that is parallel to the x-axis. So for the first one, this is the differential area here. Its height is going to be this top line, basically the top line minus the bottom line. So in terms of y, that is root 2x minus x, and then the width of the differential area is dx. So our dA is equal to root 2x minus x dx. Plugging this into the formula of the integral, plugging this into the integral in the formula, we still have this x squared times everything. And because everything else is in terms of x, it works out, but sometimes you have to plug stuff in. So expanding this, we have x squared times the square root of 2x, which is really like the square root of x times the square root of 2. So we can take out the square root of 2 and get the integral of x squared times x to the 1/2. And then this negative x we can put out in its own integral, so the integral of x cubed, because it's x squared times x. So in this case, it's going to go from 0 to 2 because that's the length of the area. The integral of x to the power of 2 times x to the power of 1/2 is, well, 2 plus 1/2 is going to be 5/2, and then this integral this integral is the same as before. So solving these with the power rule, it's going to be the exponent plus 1 over whatever the exponent plus 1 is. So 5 halves plus 1 is 7 halves. Divided by 7 halves is going to be times 2 over 7 from 0 to 2. And then the other integral is going to be x to the power of 3 plus 1, 4 over 4 from 0 to 2. Plugging everything in, we get 0.571 meters for the moment of inertia about the y-axis. So for the x-axis, we have to get another differential area, this time parallel to the x-axis. And this one, the subtraction is going to be the other way around. So because it's on the x-axis, this one is larger than this one. So it's going to be right minus left, or y minus, solving this for y, we get y squared over 2. Or sorry, solving for x, we get y squared over 2. Plugging that into the integral of y squared dA, we get y squared times y minus y squared over 2 dy. And I split that into two integrals again. So the integral of y cubed dy from 0 to 2 minus 1 half, I took out the 1 half, times y to the power of 4 dy. So solving those, y to the 3 plus 1 is y to the 4 over 4 from 0 to 2. And then the other integral is going to be y to the 4 plus 1, which is 5 over 10 from 0 to 2. Plugging in the 2's, we get 0.8 meters. For this problem, we're given the dimensions of this shape, and we want to find the y-coordinate of its centroid, the moment of inertia around the x-axis, and then k of x, which is the, I believe, the axis of gyration. So to do this, first we're going to find the area of the, we're going to find the areas, the distance to the centroid, or the y distance to the centroid, and then the area times that distance for each segment. And then we're going to use the formula of the centroid is equal to the sum of the areas times the distances to the centroids divided by the sum of the areas. Next, we are going to sum the moments of inertia using the parallel axis theorem. So each of these segments are rectangles, so the moment of inertia about the x-axis is going to be 1 over 12 bh cubed. And then to get the moment of inertia about the x-axis, because all of those will be about their respective centroids for each segment, we have to add area times the distance squared to the x-axis. And to find the k sub x, it's going to be the square root of the moment of inertia over area, the total area. So here's a table I made where I find the areas of all the segments. So this first one is 0.8 by 0.2, which is 0.16 meters squared. For this segment 1 up here, it's going to be a total of 0.9 meters away. Segment 2 in the middle is 0.6 by 0.2, so an area of 0.12, and its centroid is 0.5 meters away. Segment 3 down here is 0.6 by 0.2, so again 0.12 meters squared, and its centroid is 0.1 meters off the ground. So totaling everything together, the centroid is equal to the sum of this times this, basically, over the sum of the areas, which is 0.54 meters. So next, to find the moment of inertia, I did it for each segment. So for segment 1, I plugged in, first I found the moment of inertia relative to its centroidal axis, and then I used the parallel axis theorem to, well, I did it all in one line, but I used the parallel axis theorem to find its moment of inertia about the x-axis. So the formula is 1/12 bh cubed, so I have 1 over 12 times 0.8 times 0.2 cubed, plus the area, which I have in this table, 0.16, times the distance, which is also conveniently in the table, 0.9 meters squared, and that one is 0.13. For segment 2, its moment of inertia is 1 over 12 times 0.2 times 0.6 cubed, plus its area, 0.12, times the distance from the x-axis squared, so 0.5 squared. That one was 0.0336. Finally, for segment 3, we have 1 over 12 times 0.6 times 0.2 cubed, plus its area, 0.12 times the distance from the x-axis, 0.1 squared, and that was 0.0016. So the total Ix is going to be the sum of all of the moments of inertia that we found. And adding all those together, I got 0.1652 meters to the power of 4. So finally, to find k sub x, the formula is just the square root of the moment of inertia over the total area. So I plugged in 0.1652 and 0.4 from the sum of the areas, and I got 0.643 meters.